All right, well, thanks very much for that introduction. As Bill was saying, there's been some very dramatic progress over the last 5 to 6 years on a range of tasks in artificial intelligence. And what's interesting is that most of these advances really come from one particular type of model, and that's deep neural networks. And so that's what my talk's going to focus on. And as a result of these breakthroughs, there's been a lot of excitement in the popular media about AI and what it can lead to. And so at the end, I'll try and give some sense of the remaining challenges that stand before us if we're going to truly solve the problem. Okay, so deep learning is really a kind of revival of neural nets. And so these things have been around for a long time. They were invented back in the 1940s. And the sort of underlying principle behind them is that of connectionism. So there's this belief that somehow complicated behaviors can arise by connecting together large assemblies of these very simple computational units. And so the type of simple units that people were envisaging were these sort of idealized artificial neurons, where you would have essentially a series of simple addition, simple multiplications of the input, and then an addition operation, and then some kind of nonlinear function. And the idea, the sort of belief of these early pioneers was that somehow if we connected, enough of these units together, then we would get interesting things happening. And it turns out that has been fulfilled, but just this sheer scale at which you need to do this is something that was quite beyond the reach of the sort of computing hardware of the day. So after some, hiatus, there was a sort of revival again in the sort of mid-80s, when people finally figured out how you could train networks of these models which had multiple layers, okay? And so that's actually proves to be crucial, as we'll see, for making these models do interesting things. And around that era as well, people also developed architectures of neural network that were sort of particularly well designed for certain types of input. So for example, for images, this convolutional neural network model that Jan LeCun and colleagues at Bell Labs pioneered, essentially involves repeated stages of filtering and some kind of pooling, which mimics very closely the sort of some neuroscience insights from people like Hubel and Wiesel. And as we'll see, the models from these kinds of model actually have proven to be remarkably important in these modern breakthroughs. So the sort of modern era of deep learning really begins, I guess, in about 2011. And since then, there's been some really enormous gains in performance on a range of perceptual tasks. So by this, I mean things like computer vision, where you want a computer to understand the content of an image. Also things like speech understanding, where you want to, to be able to transcribe, someone speaking to you. And then also things in natural language processing, for example, where you want to perhaps translate between different languages. And there's sort of three key ingredients that sort of, are common to all these breakthroughs. So first is these deep neural network models. And really, they're pretty much the same models that people had back in the 1980s, except now they're just much bigger than they were before. And then the second thing is, with these big models, you have lots of parameters that you need to estimate during training. And therefore, you need lots of training data. And so with the advent of things like Amazon Mechanical Turk, it's become possible to compile data sets of millions of examples and things like that. And then when you have these very big models with lots of data, you need an enormous amount of computational power to train them. And that's where GPUs come in. So these have proved crucial as well. Now, there's been also a lot of exciting progress on a range of other AI problems aside from perception, and that's what the other speakers will focus on. Okay, so just to talk about the hardware for a second. So it turns out these deep nets are particularly amenable to implementation on GPUs. That's because basically they involve things like matrix multiplications and 2D convolutions, which are easily parallelized. And the latest generation of these cards is they're incredibly powerful, sort of 10 teraflops, which is a bit of an abstract number, but it's important to realize that's about 10 million times faster than the models people in the 80s were using, than the machines people in the 80s were using to train their early neural nets. And in computer vision, at least, the sort of breakthrough came in 2012 when Jeff Hinton and his students at the University of Toronto came up with a very big neural net. This was essentially the same kind of architecture broadly as Jan LeCun, his original convolutional neural network model from the 80s, but it was just much bigger. So it had 8 layers, 60 million parameters, and they trained it on this ImageNet data set with 1.2 million labeled examples. And because this huge model, it took about a week to train on a pair of GPUs, despite some excellent engineering work. And this is just a little schematic showing the kind of architecture of the models. You put an image in here, and then the output you have a sort of a label from one of 1,000 possibilities as to what the object is in the picture. So I'm just going to show you a little bit how you would usually use this model, and then describe how it sort of differs from the sort of traditional approaches to solving these problems. Okay, so the paradigm here is supervised learning. So the idea is you have a model with parameters that you can adjust. Initially, they start out as random, and you present input images to the model, and that passes through, and you get some kind of prediction as to the label, the object that's present in the image. Now, for each of the training examples, you have available a label that's been provided by a human. Okay, so you have some sort of ground truth. In this case, it happens that the model gave the right kind of output, so you don't update the parameters. But then you keep looping through your sort of millions of images in your training set, and sooner or later you come to one like this one, which the model says is a zucchini, but in practice is actually just a slug. Okay, and so that gives you an error signal, which you can then propagate back into the model. So this is this back propagation algorithm, which is actually nothing more really than the chain rule. And that can be used to update the parameters in the model in a principled way, so that next time that it's presented with that image, it would make the right prediction instead. And so you do this millions of times, just slowly updating the parameters of the model. And then eventually, at some point, it's sort of the performance, the objective function converges. And then you can then take the model and then try it out in a sort of test scenario. So in the test scenario, what's going to happen is you're going to take that model, the parameters will now be fixed, and then you're going to sort of take new images which it's not seen before, and then present them, and then hopefully get some fairly accurate prediction as to what's in the picture. And the key point is it's not enough for the model can't simply memorize those training examples. It has to generalize away from the training examples to these new things it'll see at test time. Now, so these models, that's the sort of overall paradigm that we're going to use them for. Now, just to contrast them with the traditional approaches, so in traditional methods, essentially domain experts would craft some sort of feature extractor that would go from the pixels to some high-dimensional feature vector that you think would be kind of appropriate for the task at hand. And then there would be some learning involved, but that would really only be for the sort of a simple classifier that would sit on top that had relatively few parameters. And that's somehow different to the deep learning approach, where you're going to really just have all stages of the model be learned. So you're going to go all the way from pixels to the class label prediction in sort of one fell swoop. And each stage of the model is going to extract effectively increasingly abstract features, which will be, ultimately then be, at the final stage, be used to then just make a classification as to what's in the picture. And during training, all these stages are updated systematically through this backpropagation. And it turns out that it's hard to get these things to work, but if you do, once you have the right architecture of model and the right kind of tricks for optimization, these models just work a lot better than the traditional approaches. Okay, so just to look at that empirically, this ImageNet is a data set, and they also have a competition that they run each year. I'm showing here the performance of the winner of each year's competition. And this is error rate, so you want to be as low as possible. So these two results I'm showing were sort of pre-deep learning using traditional methods. And you can see where they're around sort of 25%, which in practical terms isn't all that useful. The thing just makes too many mistakes to be able to use it for any practical application. And then in 2012, that paper came along from the Toronto group, and then there was a big drop-off, big improvement in performance, and so a big drop in error. And then perhaps equally remarkably, since then, in subsequent years, people have been able to sort of adjust the architecture of these models to drive the error rates down, really to sort of quite impressive levels. So now, I think the latest numbers are about 3% error. And just to put these in context, if you get a human to do this task, and it is a slightly unnatural task, because you're asked to classify 1 from 1,000 categories, and some of them are quite similar, humans get about 5%. So these models have gone in the space of about 5 years from pretty hopeless from any practical use to being really working very well indeed. And the interesting feature about these sort of changes that have occurred, the architectural changes that people have made, really there's been quite a few of them, but by far the most important really is depth. So if I overlay the depth of the winning model for each year, you can see that in recent years, the depth has really become enormous now. So the latest models have over 100 layers of representation. And essentially, people have figured out how to optimize models of that depth effectively. So it requires redesigning the architecture of each layer slightly. But if so in other words, it's the depth of the models that is sort of crucial to making these things work. And so just to talk about that in a bit more detail, so even though each layer is a fairly simple function, the key idea is that when we stack these on top of one another, we can build up very, very complicated decision surfaces. And so this is just a little example here. You can see a little two-dimensional input space. You've got red and blue dots, and you want to separate them. And you can see that they're clearly not separable by a simple linear decision surface. But each layer effectively gives you a simple linear decision surface. But this is a 3-layer model. So when we stack 3 layers together, we can see that the purple boundary that you see here, which is the resulting decision surface, is actually very complicated and does a good job of separating the two classes as far as you can. Now, of course, with the big models, there are many more layers than this. The dimensionality of the input's much higher. And that, in practice, what happens is you can learn very complicated invariances. So, for example, if you look at somehow inside some of these trained models on this ImageNet data, and then I'm just showing here patches that activate a particular channel in the model very strongly. And these ones are about halfway through the model, so they learn sort of somewhat complicated concepts, but they're not fully at the sort of object-level representation. You can see this one on the left here, this particular channel seems to like sort of concentric circles or something like that, whereas the one on the right seems to pick out sort of text on the side of objects. And you can notice it's ignoring quite a lot of, it's invariant to the background it's on. And these sorts of invariances would be incredibly hard to sort of hand code. And that's what people were trying to do before, but instead you can see these things arise naturally just through kind of basically training the models end to end. Okay, so just to give you sort of a more qualitative feel as to how well these things work. So here's a sort of typical photo you might take at your house. And I'm just overlaying the output of one of these deep nets. In this case, it's outputting bounding boxes and along with the confidence. In practice, they can also segment at the pixel level too, and you can see there's heavy occlusion, and the model still can cope with that. They can also, they're finding objects which are in sort of unusual poses as well, and so on. So that's one example. Perhaps there's another one. So this one, you can see there's some quite adverse lighting. There's people hidden in these dark shadows, and it still finds them reliably. And these, I'll just show you a little video here. So this is actually some recent work by colleagues at Facebook. So this is doing sort of human pose tracking, and this is just running independently on each frame, and you can see it's able to sort of very accurately get the pose of the individual. And these models are actually lightweight enough, they can actually run on a sort of high-end smartphone as well. Okay, so another example. This is a more challenging example. You can see occasionally it does lose track of the person. By and large, it does a pretty good job, and it gets all the people in the background nicely and so on. Okay, so shifting gears a little bit to speech. So they're essentially these same models. In fact, these convolutional neural nets prove to be very effective there. And they've completely superseded the sort of preceding technology. So people worked for about 40 years on approaches shown in blue here. And then from 2010, 2011 onwards, people switched over to the deep learning approaches. And you can see quite dramatic gains in performance. And I think what's interesting about this plot is it shows how even for the same amount of training data, you get quite a dramatic jump. Okay, so it's not just that you're using more data. Even for the same amount of data, these models are more effective. And in fact, you can see that the slope of this line is actually steeper with the deep learning approaches. So they're benefiting more as you increase the amount of training data relative to the more traditional approaches. So just to give you a flavor of what these sort of state-of-the-art speech system looks like. So this is the one from Baidu, came out a year or two ago. So this has 100 million parameters. It has 11 layers. It was trained on like 12,000 hours of speech. And at least on these benchmarks, beats humans on, by some small margin. And so this is, obviously a huge system, but, you can see that it's actually, these models can really work very well indeed. And then the other domain area where there's been a lot of progress is natural language processing. Now, text obviously has a sort of linear structure to it, a temporal structure that needs to be captured. And so people use in practice different models there, things called recurrent neural nets. And so if we just look, there's a range of different problems in natural language processing, but one of them is machine translation. And so this is a little diagram here showing how you ingest basically a sentence, say in English, into this using this recurrent neural net. And it actually represents the entire sentence as one very high-dimensional feature vector. This is the thing shown in red. Then you have a separate part of the model, which it's another one of these recurrent nets, which will transcribe this back into the target language. In this case, it's French. And so this might seem a somewhat improbable approach, but it turns out that with good engineering and some extra tricks, these things have really superseded now the sort of more traditional approaches that rely a lot more on sort of linguistic knowledge and things like that. So this is sorry, the axis here should be sort of 2014 to sort of 2016. I should say, however, though, I think the gains on things like machine translation are relatively smaller compared to traditional approaches than they are in speech or vision, where they've completely superseded absolutely everything. So these breakthroughs have enabled a whole range of different practical applications. So obviously, you've got things like Google Translate. If you've ever tried that, you can translate between all kinds of different language pairs, even ones where you may not have too much data available, or they're uncommon ones, rather. There's also things like speech recognition on your smartphone now works very well. And in fact, without realizing it, you're probably using some of these deep learning models every day, because pretty much all the internet companies use them in some shape or form. So Facebook, Google, Amazon are all using them under the hood. Facebook, for example, there's about 1.5 billion images a day uploaded. And each image is passed through 2 of these deep nets, in fact. So there's one that does the face recognition, another one that does object recognition and finds offensive content and things like that. And I guess one that there's also a lot of attention on at the moment is self-driving cars. So if you want your car to drive safely, it obviously has to reliably perceive the environment around it, no matter the weather condition, no matter the lighting, and so on. And these deep learning methods have been absolutely crucial to kind of getting the perception up to the level needed to do this. Now, I should also mention that these deep models have actually starting to have a lot of impact in science, I think. So you're starting to see applications now in particle physics, astronomy, chemistry, and genomics. And I think the impact of these is going to grow a lot in the next few years. And of course, a huge potential application area is medicine, and that's what Suchi is going to talk about later today. Now, I just want to take a step back and look at some of the sort of underlying sort of principles that make behind these models. So, at a sort of philosophical level, previously, the human effort went into designing the feature representation. The domain expertise would be used to sort of craft features that were appropriate for the problem at hand. But in deep learning, that's gone away. So now we're learning those features, but humans are still in there because they really need to design the architecture of the model itself. So in other words, the number of layers, how many units in each layer, what the nonlinearity should be, and so on and so forth. And it turns out that if you just take a generic structure of neural net which doesn't have any particular, which is agnostic about the type of input signal, they don't really work very well at all. And so the real success stories have come when people have managed to find architectures that are particularly well suited to the domain at hand. So for example, these convolutional networks that I was talking about, they exploit the fact that you have pixels are on a regular 2-dimensional grid, you have local dependencies and things like that. And so when you come to new types of data, say you had data in the form of a graph, it's a little bit unclear kind of how you would apply these things. And so actually there's quite a lot of interesting research now on, for example, neural nets that can work in graph settings and things like that. So humans are still involved in the design of these things for sure. It's not like the learning, it's not like they're completely learned. It's also important to kind of highlight issues that these models have. So despite the amazing empirical performance, I think from a scientific point of view, it's very unnerving that there isn't really a very good theoretical understanding of what these models are doing. We don't have things like performance guarantees, which could be important in certain settings, like self-driving cars and things like that. And the reason is that it's just very hard to analyze. A lot of the mathematical tools that we would use, unfortunately, just don't apply in these settings. We have very high dimensional inputs and parameter spaces with highly non-convex objective functions and so on. And so, there's a big gap at the moment between theory and experiment. But the good news is that there's lots of very, very smart people thinking about these things and trying to work out what's going on. I think it's also worth pointing out that these models are actually quite difficult to inspect what's going on inside them. So if you have some network that gives some prediction about, say, what drug treatment should be used in a given setting, it's hard to look at these models and say, well, exactly why is it recommending that? And that is different to other types of machine learning models. So if you have things like graphical models, in those, each variable in the model does have an explicit meaning in the real world. So I think that's one area that's one shortcoming. And then one that I think should be, I've been alluding to, is this need for lots and lots of labeled data. So you have to have humans at the moment go in and annotate these big data sets. And it's not always going to be possible to do that. And so I think one big research area that a lot of people are working on, and most people feel is sort of fundamental to solving AI, is learning without labels. This is called unsupervised learning. I think in practice you would always have a few available, but the point is you would need to use the majority of the examples without labels to somehow learn some structure about the data. And I mean, just to motivate this from a very practical point of view, in many settings in the real world, the distribution of categories is very uneven. So you have many, many categories with only a few examples. So for example, if you look at Wikipedia, if you look at the distribution there, this is a log plot of frequency versus rank. There's a lot of categories for which you only have a handful, a dozen or so training examples. And so clearly, with models with millions of parameters, it's going to be difficult to train those directly. So this is one big thing people are thinking about at the moment. There's also a sort of slightly different motivation. This is something that comes from Jeff Hinton, and he points out that our brains have about 10 to the 15 connections, the synapses in our brains, but we only live for about 10 to the 9 seconds. And so if you want to set those connections, you need to somehow get about 10 to the 6 bits per second of information. And there's clearly not enough, that you don't get enough from your mother saying, here's a spoon and here's a cup. That just only gives you a few bits of information. And so in some sense, the learning mechanism that we use can't be completely supervised. There must be some sort of other mechanism going on. And really the only other source which has enough information is the input itself. And so if you look at a lot of unsupervised learning approaches, essentially that's what they're trying to do, is sort of predict the input in some constrained way. So another whole area which I think is very active area of research is this notion that you need to sort of reason and plan. So perception is just one aspect of things. You need, in the real world, your robot needs to act. And the question is, what action should it take to achieve the goal it's supposed to do? And so to do this, it's really got to be able to essentially predict what's going to happen. And so you need, in some sense, your robot to have a little simulation of the world so it can try out in its simulator a whole bunch of possible sequences of actions and decide which one will be most appropriate. And so there's a lot of work at the moment on this kind of thing. And so Michael's going to talk more about this type of learning. So just to wrap up, there's been a lot of progress on these perception tasks, and there are many practical applications that are possible now. But there's still many unsolved problems, and we're going to need new algorithms and approaches to tackle them. And so there's a lot of research now in both academia and industry on these. So I mentioned two of them. There's also interesting things like program induction. And I think it's very unclear how to go about solving these. We don't, despite all the sort of excitement in the media, I think most serious researchers wouldn't want to give any firm timeline about when any of these problems might get solved. Okay, so I'll just finish there and take any questions.
Thanks, Rob. We have time for a couple of questions between the speakers, and then I'm hoping we'll have time at the end for a more general discussion. But are there any questions that people would like to ask Rob?
Rob, right here.
Yes?
Now you're supposed to wait for, we're getting a microphone there, so if you could go to the microphone, or maybe it will come to you, I'm not sure.
That was really good. I was wondering whether you mentioned that the neural nets were sort of unpredictable. I guess are they as badly behaved as sort of lots of other difficult problems like NP problems?
So, I mean, the unpredictability, well, they're not really unpredictable in the sense that they are sort of, if you make small changes to your input, generally the output will, behave in the right way. It won't change too much. I mean, they are sort of continuous things, so that, this is actually one of the other points I didn't raise, but, at the moment they're all continuous so that you can differentiate, and that's how they're trained. So, yeah, they don't have a lot of relation to kind of discrete problems like NP completeness or anything like that. I mean, there are some interesting, yeah, I think that's right, just leave it at that.
Good. Question here.
Yes, several years ago, I posted pictures of sculptures on a mother of heads, but they were clearly stone. Any human being would know they were stone. And Google immediately asked me to name them. And within the same time frame, there was an exhibit at the San Francisco Modern Art Museum of what the Steins had collected, and there was a picture of one of the Steins' rooms, and it had what was obviously a mannequin head, like to demonstrate it, to wear a hat, and it said unknown woman. And I said, no, there's no way there's a body there behind, it was a mannequin on top of a dresser. So I assume that by now, Google wouldn't ask me that, and the Modern Art Museum wouldn't have that mistake. So just wanted to know what has been done to improve understanding things like that.
So I'm not sure if people, right, so it depends a lot on again, there is, as I said, the algorithms require labeled data, so it depends a little bit on the labels that have been provided. So if people have manually, annotated some of these sculptures as actually being human faces, then the algorithms will learn that. I'm not sure if the latest algorithms that are used in companies like Google and Facebook actually have, an explicit negative set of these sort of, human-like, face-like patterns. Probably they do, actually. I mean, but you can mess things up if humans are consistently tagging them. Then it'll overrule that. So.
Let's have one last question now. There.
You showed this is 6 connections, 6 million connections per second, but I thought a lot of the neural planning in the brain is removal of connections and pruning. And I'm wondering whether you have models that involve starting with connections and then eliminating ones that are inappropriate.
Right, so that's true. So most of these models do have, in practice, they're over-parameterized, so that typically when you train them, you'll see that many of the weights then actually end up having sort of, essentially negligible impact on the final result. And indeed, if when you take a fully trained model, it's possible to compress them quite heavily, which is indicating that there's a great deal of redundancy in these things. Interestingly, you can't train them using compression because somehow the over-parameterization is very important for the optimization of these very complicated models. That's an interesting thing people don't understand too well.
Thank you. Let's thank Rob again.